In this video, I'm going to go over the differences between Boolean algebra and prepositional logic. Now, there's a slight difference between them, but they pretty much are the same, except there's going to be different symbology and the way that laws of work in truth tables, they come out kind of exactly, but the conventions are slightly different. So I'm going to go over really the conventions. If you're unsure about how I got to all of this stuff, in this lecture on prepositional logic versus Boolean algebra, you can kind of reach out to me. Again, I'm just trying to go over more of the conventions. Now, on Boolean algebra, we have ones and zeros, which is why we also use them in prepositional logic. But one doesn't mean, on, and two doesn't mean false or true and false. We think of one as being on, or active, and zero being off or inactive. So it's kind of like when you have a light switch. And if this light switch is turned down, then we would say, well, okay, this is now in the off configuration. But if you have a light switch and it happens to be on or up, you would say that it is in the on configuration. Pretty simple. So it's one that's out there that could be an example of a system. If you think about another system, like for example, security system, I mean, like your house or apartment, you typically have an alarm that would be active, like if all the windows are closed. So you would want all the windows to be in an off state. Or, perhaps you have a machine that dispenses a drink, a vending machine. Well, while it's dispensing a drink, it's turned on. So that function, while it's not dispensing a drink, would be turned off. So you basically have a system as well. So it's the same result as prepositional logic, but the symbols and the connectives of these things are all slightly different. So let's talk about those connectives here in a little bit more detail. I'm going to compare two sides side by side. So here are the different operators. In prepositional logic, when we want to do something, like for example, not on P, we use this negation symbol. In Boolean algebra, typically the first new thing that we use lowercase letters x, y, and z. So on, we can use the capital letters too. But when we have a negation, we put a little line on top. So this would not be x or not x, or you could think of it like x bar or x complement. Now for or, we have a different symbol. We have this symbol that is P or Q. So we use the V. This thing is called a wedge. And we put it in between the two, in this case, in digital logic. Now in Boolean algebra, we have X and Y. And we use a plus symbol, right? So that is, why in some systems of prepositional logic or, introduction, this is called addition because it uses the addition symbol. In Boolean algebra, it's a little bit different. For here we got P and Q. Typically we use the caret or the ampersand in digital logic. It's a little different when we just write these side by side. That's also used here for set theory and probability. So like for instance, we have in set theory and discrete math, typically we would write P and Q, P intersection Q, but in probability it just uses PQ. It's sort of the same idea with logic when it comes to Boolean algebra versus prepositional logic. Now the implication is the same, which is nice. So if you have P arrow Q in Boolean algebra, we can just do the same. Just the same thing with X and Y. But typically, how we would write this instead is we would use its equivalent. So instead of writing X arrow Y, we know that this is the same thing as not X or Y. So perhaps instead, I will write this on the side. We might write like here X plus Y, and then X gets a complement, so that would be the same thing as not X or Y. Exclusive, or uses the same symbol for either one. So whether we have XY, whether we have PQ, we use the little circle with a plus sign in it. So this is an exclusive or this means either one of X or Y is true, but not both. Got it? You can always write it in its equivalent, which is not X and Y, or X and not Y. And for its equivalence, there is a very slight difference here, but depending on the logic system you might use the same symbol. In Boolean algebra, you would use 3 lines to be equal to, and in prepositional logic, we would use the double-sided arrow, so a very slight difference here, but essentially these are really the same things. But the differences between Boolean algebra and prepositional logic are still translated the same way, but the symbols are slightly different, as you can see here. Now, another thing I'm going to point out here is, if you can imagine, I want to take, the negation of something, and I want to take not, and in prepositional logic, we would take these two things and put brackets beside them and put a negation outside. In Boolean algebra, we simply would put a bar above both of these. So, there is a little bit of a difference. The difference between, I should put these really close together so I can see them. Okay, now there's a difference between these two things. So these are not the same thing, not X and not Y. So this would be like saying, not X and not Y, while the other one right here is more like saying not X and Y. So there is a difference with how we use the bars, just to point that out. Okay, now let's go on to a truth table here. Now these are also the same as their own prepositional logic, but typically in digital logic or Boolean, we start with the false cases up at the top and the true cases at the bottom. So, when I teach courses on this, for prepositional logic, I always get a couple people who like this because they're brought up, more as computer people. So it drives me kind of a little bit crazy because I'm not used to seeing this because I don't really work in that way. I more work in digital logic. But let me show you how this is done in digital logic. So when we take not X, of course, this is just the opposite value of X. So if X is 0, then not X is if X is 1. Then not X is 0 right here. So with X or Y, X plus Y is false. If I have an I is false, if both X and Y are false, but it is true in every other case. So it's true if X is true, or if Y is true, or if both are true. Now for X and Y, it's only going to be true when both X and Y are true at the same time, and it'll be false in every other case. So you'll notice by now these are just the truth tables for prepositional logic, with the formulas below that they're reversed top to bottom. With X arrow Y, this is the same thing as saying not X or Y. So this is going to be true. True when either we have X is true, so in rows 2 and 4, or when X is false, so rows 1 and 2, it would also be false. Whenever you have X is true and Y is false, it's the same thing as P arrow Q, and this is an exclusive OR, and is only true when the values of X and Y are different. Got it? So it's true in the 2 middle rows and false in the outer rows. And the biconditional equivalence is only true when the values are the same. So when X and Y are both 0 or both 1, and then it's false. When you have differing values, pardon me. So when you work with digital logic, you get to think that's okay. Well, this isn't a 1 to 0, 0, 0 truth table, and it becomes, the 0, 0, 0, 1 truth table, and, so just keep that in mind. This is just a convention, of course. You can write it the other way if you want, but people who work in digital logic may not be too happy with the way that you do it. It's just that you would take conventions of the field that you're in, and this is how the convention would work. All right, so the last thing I want to talk about here are some of the laws of this. So anyway, what you can do is sort of aid ourselves, is think about what this means in terms of prepositional logic and how does this translation work. For example, x plus x. This is the same thing as saying, x or x. So when we think about, x or x, this is called idempotence, or just gives me x back, omnipotence, pardon me. So this is what we get in digital logic. When we take x or x, we get x. So if we take x or not x, well, we know that this is a tautology, so it comes out to be true in our system. So in digital logic, x or not x, this comes out to 1, where 1 is true. What we have here, like x or a contradiction, when we get this. So when we get x back, since it will be a true contradiction, it's always false. So x or 0 is the same thing as saying x. Now, what about x or true? So this is true when either x is true or true is true, which is always true. But the tautology is always true when we get the tautology out of it. So x or 1 gives us, 1. X or 1 gives us 1. So x plus y, we have the commutative property. So x or y, x plus y is the same thing as x plus or x or y or x. So let me put those around, and let's go to the last one. The last one is De Morgan's law. So this might not be obvious, but if we have P or Q and R, in fact, maybe I should just put the same letters that we have in digital logic, but in capitals. So X or Y and Z, we know this is the same thing as saying X or Y and X or Z, right? So we're just using the De Morgan's law to expand what we get, so we see the same thing with digital logic. So either we get here an X plus Y, or it's X or Y, and we get X or Z. So I have to make sure that I'm using plus symbols instead of the or. All right, so this one looks a little weird because you're probably thinking, arithmetic, x plus y times z does not expand this to Boolean algebra, but it really kind of does. All right, so now the laws on the right are the same thing, except that instead of using ors, we're now using ands, right? So if I can think of it along these lines here, let's just change the symbol here and see what happens to speed things up a little bit. Let's see. All right, so if I have x and x, well, that's just the same thing as x, so that gives us x back. So if we have x and x, well, we get x, right? Seems right. So if we get x and not x, well, this is always a contradiction. This is a false, and you cannot have both x and not x at the same time. So in Boolean algebra, that gives us a 0 or a false. So if we have x and the contradiction, well, it has to be, both of these have to be true to get an output. But if the contradiction is always going to be false, which means that this will always be false, this will always be false. So x times 0 is always 0. X is true. Well, it's always going to be true, right? So all the time, because it's always going to be true, so we're going to always get x back in this case, and x is true. Well, it depends on the condition of x. If x is true, it'll be true. If x is false, then it'll just be false. So in Boolean algebra, that gives us x back, right? So when we have the commutative property, so if we have x and y, we also have y and x. So De Morgan's law works the same way. This one's a little bit more arithmetic friendly. So if we have x and y or z, we can use De Morgan's to get x and y, or x and z. So when we expand this out in Boolean algebra, we're going to get xy, right, plus, wait for it, xz. It's the same thing. So let me clear this up a little bit, and let's get some of these things out of the way. We can see our results, and the nice thing about this is really that you can see in some of these cases that it's very intuitive, from a regular algebra how this works. So for instance, in the case where we have x plus 0 being x, or x being false being x, this just follows naturally from how addition works. The same with x times 0, right, giving us 0. That's x and false, gives us a false. It's the same way with x times 1. We say x and true, we get x back. If we take a look at the commutative property of both, it works the same way. And the only one that's a little weird is saying that x plus 1 gives us 1. And this is kind of a weird one down here. But this still follows how actual addition and multiplication work to some extent. So don't rely on that as a fact for how this stuff works, or maybe just a trick to help you remember everything. But it's a connection that you can make in your head if it kind of helps you think about this. Anyway, I don't have anything for us to really do other than the differences between prepositional logic and digital systems. So we'll do a little bit more about this in a later class. So thank you for making it this far, and please reach out to me with any questions. Thank you. Bye-bye.